Good afternoon to everyone. Thank you for joining today in this event, Women in Mathematics Seminar. So first of all, we'd like to thank the respective heads of departments for joining us today, and the lecturers and other members of staff from the Faculty of Science and beyond for being with us today. Thank you as well for the students from the sixth forms who have joined us today and who have received our invitation. Have come. Okay, so today is International Women in Mathematics Day. And this day is in honor of Maryam Mirzakhani, who is the first woman mathematician to win a Fields Medal and was the only one. She was born on this day in 1977, but has unfortunately died due to breast cancer. But still, this day is celebrated throughout the world in honor of her achievements, in honor of her birth. To cut a long story short, this seminar shall delve deeper into the lives of 6 female researchers who are either mathematicians themselves or use mathematics in their research. So we will have the first panel, which is comprised of the 3 female mathematicians of our Shriha, Dr. Beatriz Zamora, and Professor Cristiana Sebo with us. And this shall be moderated by Ms. Marietta Karabot, who is the PRO of the Malta Mathematical Society. And afterwards, we will have the second panel comprised of researchers or lecturers that are part of the Faculty of Science or were part of the Faculty of Science, but use mathematics in their daily research. Okay, so what's in your hands? Marietta.
For our first, we will have Prof. Irene Shriha, who is a lecturer and researcher in linear algebra and graph theory. And we will have Dr. Beatriz Zamora, who is also a lecturer and researcher in set theory and analysis. Online, we will have Prof. Cristiana Sebo, who is a lecturer and researcher in mathematical modeling and biomathematics. I invite you both to join us. Hello, thank you for joining us today. It is truly an honor to have you with us today. You are some of the finest mathematicians that we have. So let's start off by asking you this relatively simple question. What attracted you to mathematics?
I always liked playing. And that's how I look at mathematics. I'm all the time playing with ideas, connections, puzzles, try to solve problems. I was very excited when I started physics in Form 3. And I chose it by accident because we had to choose from housecraft, which I hate, geography and history, which need a lot of studying. And I didn't know what physics was. So I said, most probably physics is something that where you don't do anything. So, and that's what attracted me to mathematics, to physics actually, and mathematics. And then I was overjoyed to see, to connect physics with maths. So even as a young girl, I used to really get a kick from seeing a connection between mathematics and physics at that time, and now between mathematics and anything in life, because everything that is structured is backed by mathematics. I also enjoy a great deal seeing the spark of students when I'm teaching, you know, the spark in their eyes when they understand something, you know, you see it, I've understood, sort of, you know, a silent glance, beautiful, and it gives me great energy. So I go out of a lecture room smiling and thank God forgetting all the problems of life, because obviously I think everybody is overwhelmed with today's problems. I've always had problems, and my way out was always to go and mathematics, to forget. So now my area of research, because you said graph theory, actually my area of research is more linear algebra. But I use graphs because graphs are so nice to draw and you see them. Whereas with linear algebra, you just see a lot of symbols. So I draw a graph, and from it, I see sort of matrices on graphs, and how do I change them? And it so happened that I came across a problem that had been, is now about 70 years old, which is, if you have a matrix, does it have redundant, if you have a real symmetric matrix, so a graph, does it have redundant columns? For the mathematicians, does it have a kernel, a non-trivial kernel? And I said, this is really easy. You find the determinant, put it equal to 0 and check, you know. And, but then I was saying, but in a graph, can I see it? Can I see substructures that, you know, tell me, yes, this must be singular. I call it singular, not I, it's called singular. Does it have substructures that tell me immediately that it has problems? And then it turned out that this problem had been researched by chemists since the 1950s. So chemists, when they saw my papers, approached me and they said, can you shed some light on benzene, carbohydrates, and, you know, and so that's an area of research I do now.
Okay, so going back to that question, well, to be honest, I entered to study mathematics at university, not knowing very well what was mathematics about, yeah? I knew I like, you know, to numbers, and I started late, you know, kind of really getting into maths. But the more, you know, I learned and what was mathematics about, I mean, the more I fell in love, let's say. One thing that really kind of attracted me once I learned, you know, how mathematics work is that it's different from other science in the sense that you start from basic principles and then you prove things that we call theorems. Probably people here know what is a theorem. And I mean, we start from principles that, you know, we are certain about that there is no dispute that those are truth. And then you prove theorems, and then the theorem stays forever. Nobody can come, well, unless you go back and say, you know, your principles are wrong. You are certain that what you will prove stay forever, right? Unlike some other sciences that, you know, you do some experiments and then you do your hypothesis and you have some results. But if someone else comes with a better, you know, experiment, and the science can change, right? But when mathematics, you have more certainty that, you know, what you prove stays there, you know, it's yes, and you are certain what you prove stays there. And then, you know, as Irene said, you know, I always, you know, and we all know that mathematics are everywhere. Kind of everybody, our teachers tells us, you know, mathematics are everywhere. But also, you know, when I started studying more, I was amazed that we can study infinite sets, right? Even things that, you know, we don't exist in real life, you can study them. You can prove things about them, right? So that also attracted me a lot, the study of, you know, things that are not even like we don't see. So those are some aspects that, you know, kind of attracted and made me stay studying mathematics. Yeah.
Yes, hello, can you hear me?
Yes. We can.
First of all, I have to apologize for not being able to be there with you physically, but I'm very glad that I managed to join you online. What attracted me to mathematics? Well, it was a long journey, and it started with, I've always been endowed with an analytical mind and a vivid curiosity, which was somehow nurtured by the fact that I grew up in a family of scientists, and studying sciences, exact sciences, was a bit of a natural choice for me. I received, a proper education as a little girl. My parents brought me to piano lessons and ballet classes, but at the same time, my parents were the ones who actually encouraged my attraction and my fascination with sciences, and they actually praised my exceptional performances in the national and international physics Olympiads. And although deep down, maybe in their hearts, my parents would have liked me to pursue a career in medicine, as it would have offered me a much better life from the financial point of view and a better status in the society. They actually eventually fully supported my decision to study theoretical physics and then applied mathematics at undergraduate and postgraduate levels. So it was a natural choice for me. I grew up with scientists in the house, and I've been surrounded by science books, and yeah, so that was why how I ended up here. Yes.
Wow. Those were some three very interesting stories on how you ended up being attracted to mathematics. I would like to ask you all where you studied mathematics, and to my knowledge, you have all, I think, studied abroad at some point in your lives, and I think it would be interesting for you to tell us if you have seen any differences between maybe teaching styles abroad and teaching styles here, or any general differences between universities abroad and the university here. So.
Right, so as a student, I was here for BSc and Masters. And then I went to UK to do my PhD. And I noticed differences, yes. For one thing, the students live on campus in the UK. And the amount of studying they do is very little, I can tell you. I mean, and even I attended some lectures to see the style and so on. I would say in Malta it's much better. But I mean, I'm part of the teaching community, so I may be biased, but I think, we care for the students a great deal. I think the students agree with me on this, that we do care a lot for them. In the UK, it may be the British character, but they're very strict at the beginning, but then towards the end of the course, they make sure they pass. So if they're not studying, they hound them. Come for the tutorial, come for that contact hour. With us, we get so many requests for contact hours, we say we have to stagger them or maybe do a class tutorial. But with in Britain, this was something I noticed. That girl isn't going to make it. She's not studying. It's not that she's not good, but she's not studying. Yes, they take care in that way. So I don't know what is better. Both have their advantages, in fact. That's the truth.
Well, undergrad in Mexico and my master degree in Mexico as well. And then I studied in Canada, my PhD. There are many differences, even more in Mexico, yeah, from here. Well, one that I can think about is that, you know, the lecturer there was free to pick, you know, the mode of assessment. And many of our lecturers, for example, did like kind of open book exams, right? So you had to, you know, really understand the material and like that. And sometimes we were like 4 hours sitting in the exam. So it was, you know, yes, open book, and we were not able to discuss, but yeah, that kind of, I still remember, and it was very different, right? That we had all the time, we had all the time, literally, right? There was no restriction on time. So it was a bit challenging, but I think we learned a lot from that. So that was a big difference in Mexico. In Canada, what I enjoy a lot is that we had, among the graduated students, we had a seminar where it was just for students, and or supervisors were not allowed. It was kind of a rule, right? But it was really good. I mean, that got us prepared to, you know, explain the topic to each other, and sometimes, you know, help each other. And also at some point, you know, when we were ready to graduate, we had to give talks in the, you know, in the seminar for, you know, for everybody. So it was, I really enjoyed that part, and I think it was very useful to have. Yeah, those are the few things that kind of, I still remember that, yeah.
Right, okay. I did my BSc and MSc in theoretical physics back home at the University of Bucharest in Romania. The teaching style of my professors was very much old school, in the sense that we had blackboards and chalk, and they would come in the lecture room, they would turn the back to us, and they will start filling, you know, the blackboards with formulae and everything. There was very little interaction between the students, us, the students, and the professor. From time to time, he might or she might ask a question which very few of us probably knew the answer of. And then I also, part of my MSc, I spent a little bit of time at University of Mainz in Germany, but I was mostly doing research at that time. And then I did a PhD at the University of Montpellier too, in France, in the south of France. I was a research student at the time, so I was not, you know, taking any classes as such, but I had to teach. Actually, while being a PhD student, I had a very prestigious scholarship for doing my PhD studies in France, and a requirement of this actually scholarship was to teach. And also I got at the same time my certificate for teaching in higher education. I had a training, a pedagogical training on the side. And the style in France was very much at the time similar to the style of teaching back home in Romania, in the sense that the professors and the students, there was a big gap between the professors and the students, and we interacted very little with the students, and the expectations actually were extremely high from the students, and they had to basically work alone. And then I moved I taught at Oxford Brookes University in UK for 11 years. So I experienced the UK system as well, the teaching system as a lecturer, and that was extremely different. That was actually a system where we could interact with the students. The classes were very animated in some sense, that the students contributed a lot, and not also that they contributed a lot, but they took advantage of the contact hours that we offered. And every day during my contact hours, I used to have queues of students to come to see me to clarify everything that was maybe not clarified in class, or they had additional questions, and that helped the students tremendously. By taking advantage of these contact hours, many of them actually developed and became very good scientists, willing to pursue careers in academia later on. And I was very pleased with that. I also taught on and off and on basis for a university in the States, for Florida Institute of Technology. And that teaching system is very much similar to the UK one. And then I came to Malta, and I'm trying to basically adopt the same teaching style that I developed in UK, in the sense that I want the students to contribute to the class. I want the students to answer the questions and actually help me to help them to put in order their mathematical reasoning. And and it's true, a remark that Irene made, which is very true. The standards, the teaching standards at the University of Malta are much higher than the teaching standards in any UK university. And I can tell you that the level, there's no comparison. So that's something to be proud of as an institution and as a department, that we managed to teach such high standards. Yeah, that's all from me.
So thank you, all of you, for this wonderful insight. I think what's most important here is that student participation is one of the most important things in a lecture, and for the students studying career as well. I mean, as students, when we participate, or in class, or we try to work stuff out in our free time, I think that's when we are more prone to succeed. And this is possibly a message for future university students that we have with us today. Don't be afraid to participate in your classes, in your lectures, because that is how you learn, as our lecturers and researchers have told us. So here is a big question. Were you always certain that mathematics is your field? I think mathematics isn't an easy subject, and sometimes you're working on a problem and you can't figure it out, and you spend 2 hours and you don't arrive to a conclusion and you're on the brink of giving up. Are times like these where you think mathematics isn't for me, I might as well just pursue something else? So what do you have to say about this?
At the beginning, when I started my university studies, my family, at the time, it was very different. We had to pay for university tuition. Anyway, my family's aspiration was that I'll be a chemist, a pharmacist. So I went in for chemistry, biology, physics, and basic mathematics. And on the side, at the time, the rules were very free. And my friends, my immediate friends, one of them, my husband, was doing mathematics, and I used to go in for those lectures. I loved them. You could do the exams if you want to, and I did 5 exams. I remember I did all the chemistry, all the biology, all the physics, all the maths, and all the applied maths at that time. And and I was called by the dean, and he told me, do you know what you have in physics and maths? I said, no, I'm not interested. I want to know whether I passed chemistry, biology. I want to become a pharmacist. He said, forget it. He said, you did very well in chemistry. And of course, those are the only subjects I studied, actually. But sorry, Sandra, but it's so difficult. And I used to sleep on the book with those difficult names, and maybe because I didn't know Latin, possibly, and because the nomenclature was so difficult, and chlorophyll, and I don't know, and if he told me, do you know what you have in maths and physics? I said, oh, did I pass? Oh, you have, and it was, anyway, almost full marks. So he said, look, and I said, these are what I want to do. I'll do nothing. I'll do maths and physics. I thought I would do nothing, you know. But then, of course, you have to work hard with maths. And if you love it, you enjoy working. So it's not, there's no problem there. So actually, your question was, can you remind me? Deep down, yes. But as I told you, I mean, there could be pressures elsewhere, and anyway, but I never regretted choosing that.
Okay. As I said, I started quite late, you know, kind of studying really mathematics. I always knew that I wanted to study something with numbers, right? In fact, you know, I was about to study to become an accountant. I say, right? So then, you know, last year of my high school, we took some course, and it turned out that, you know, I hated it. I had to, back then we didn't computer, so we had to, you know, fill all these, you know, books, and I always cheated, and I hated that, right? It's like, no, I don't want to do this. And then we started studying, for example, formulas to calculate things, yeah? And then we started studying probability. I remember that course. And I said, okay, then I started getting more interested. And I was lucky enough that, you know, I talked to my teacher, and I told him, you know, how I felt and like that. And he encouraged me to study maths, you know. And I was a bit, you know, hesitant because I wasn't prepared for it, because I never studied at that time calculus. So I studied university without any calculus, zero, right? Without, you know, well, I had an idea what things like that. But the more, you know, I got into it, I mean, it was difficult at the beginning, but, you know, the more I got into it, you know, I, you know, stuck with it, because I started seeing how beautiful, you know, mathematics were. So yes, no, I didn't always knew that mathematics, but because I didn't have, you know, the exposure to you know, early enough to mathematics. So yes.
So were you only certain that math is your field?
All right. I've always liked mathematics, and I owe this to my father, who was a brilliant high school teacher of mathematics. And I remember that ever since I was a little girl, I used to work problems with him, you know, from a Russian, a translated Russian gazette of mathematics. And there were difficult problems for my level, but even for my father, you know, some of them, you know, required a lot of thinking, and we liked doing that together. And this is how we spent some of the afternoons. And but as being a rebel, and I discovered physics on my a little bit later in my studies, and I was very good in physics. And I mentioned to you that I used to go to the international Olympiads of physics and the national ones. I thought that I found my niche subject. My father was a teacher of mathematics. My mom was a teacher of chemistry. So I was very happy that I found a subject which was just my own, and nobody could actually control me. And so I pursued physics at undergraduate level. But after that, you know, during my MSc and then during my PhD, I realized that actually I liked physics for the mathematical actually apparatus behind, and I liked to just play with formulae and with numbers. And I was actually made for mathematics rather than physics, and I decided to change. Yeah, so my PhD was in applied mathematics. My only probably, I'm very sorry that my father didn't live to actually see me transformed into a mathematician. I think he would have laughed to death, because I did my BSc at the Faculty of Physics in Bucharest, and that was outside Bucharest. We had a nuclear reactor, therefore it had to be, the faculty was near the nuclear reactor outside Bucharest, and I used to commute every single day, long hours to get to the faculty and back, while the Faculty of Mathematics was bang in the middle, in the center of Bucharest, and I could have walked there. But anyway, so yes, it wasn't, I've always been fascinated with mathematics, but it was not my first choice from the very beginning. I decided a little bit later on to pursue a career in mathematics.
That's beautiful. So let's move on now to your research areas. So what was the first research project that you worked on? And did you have any researchers, and maybe specifically female role models, that have helped you along the way in your journey in mathematics?
Rather than, okay, role models, my role model is Emmy Noether, you know, the famous mathematician who did so much in ring theory, modules, etc. She wasn't allowed to attend university because she was a woman. Many of you are much younger than I am. I did pass through quite a number of obstacles as a woman, because I was seen as, you know, sort of not fitting in the role. As a student, I finished as the only one in the course. As a lecturer and now full professor, I spent a long time as the only woman in the Faculty of Science. But I was the only one in the Faculty of Science who was, I know Pauline was a lecturer, but when I entered, I think, I don't know, but there was a time when you left. I'm not sure. No. But in my department, I was for a long time the only one. And I did feel that sometimes I was seen as sort of, they didn't know me as a student, because if they had, they wouldn't think that. But I'm sure that some thought, you know, what can she do? She's a woman, because that was the mentality. I don't blame them. That was the mentality. Her place isn't here. I won't recount stories, but for example, you know, they would say, if something crops up, if my son had to be taken to hospital, I have to take him. Then why doesn't she stay at home? You know, I mean, that was the mentality. I don't blame them. It was the mentality in Malta, and thank God, with time that changed. But by now, my children are grown up, so I won't benefit from that. So, yes, my research, what was my first research? My first research is what it is now. You know, I kept on, if an idea comes to my mind, mostly related with linear algebra, I translate it to graphs and to see them as matrices and different types of matrices and coding graphs. And then, so my three main topics at the moment are seeing substructures. So you have a network, a graph, and you don't know what it is, but you have data of substructures. So you have missing data from the parent, but you have a lot of data from the daughters, right? And can you guess or construct what the parent is? So that's reconstruction. And I do it with more with eigenvalues than with the actual graph. But this has applications in archaeology, in genome building, and so on, right? So there are applications there. Chemistry, chemical, now we have nanotechnology, we have these small carbon molecules. Fullerene was discovered in 1987, I think, 1987. So, okay, most of you were born. For me, 1987 is still like yesterday. For you, you weren't born yet, many of you. But very, very recently, you see, because before we used to think that diamond and graphite, what we use in pencils, are the only forms of carbon, and the amorphous carbon, we used to say. And to tell you what it is, if you ever had a spiritera, what do you call it, a burner, and you get everywhere full of soot, that's carbon, amorphous carbon. So that's what we used to say. But then these were discovered. They're beautiful, they're spherical or elliptical and so on, and they're very strong, you know? And the chemistry and physics community were thrilled with these, and there are industries, you know, constructing graphene, these bags that are really light, you know, they're made of these carbon, and then it's stronger, it's very light, but it's strong, 6 times stronger than steel. So they're using it in construction. Bulletproof vests, for example, that they're light. So before they used to use lead, imagine, and armor, you know, like the Knights of St. John with that heavy armor, and they have to fight. And these are really, and they can be all, for me, they're a matrix. They're a matrix. And I look at the matrix, I look at the eigenvalues, then I check physics papers, and they say, right, if you use it in a circuit, so you put it, this small thing in a circuit, and to put it in a circuit, of course, you either use gold wires or a spark, you know, like lightning, tunneling, they call it, you know, spark that electrons go in at one. Will the electrons go in out at the other end? Does it conduct or not? And if it doesn't conduct because they expect it to conduct because of its structure, because carbon has valency 4 and only 3 are being used, and that's in those structures. So there's one that is free. It should contribute electricity, but sometimes it doesn't. And why doesn't it? And that's the study I did. So that's chemistry. And then yes, walks. I love walks. And here I saw Alex, who was my PhD student and now, of course, graduate, who loves walks, and we work together with walks. So you have a network and you walk on the network along the edges, and they tell us a lot of, they give us a lot of information, even related to sociology, to engineering control. Alex studied control in engineering, and many other. These walks are beautiful. I mean, because, and then there are some of the eigenvalues, and you say these are the only ones that will contribute to walks, and the others not. So it's still, all these are open problems. They're not solved yet. None of them are solved. So we're still working on those. And I have a project at the moment, so, and I am working on that. Sorry.
So, you know, I have been changing the area a bit. When I started research in set theoretic topology, I in something called group, something on set theoretic topology. And I had a male mathematician. Perhaps he's not very well known in general in mathematics. He's very known. Maybe some people here have heard of the book of Walter Rudin from Analysis. So his wife, his name is Marie-Hélène Rudin, and she's very well known in the area of set theoretic topology, right? So yeah, that was kind of a role model when I heard that, you know, her, she saw this conjecture, you know, like many people, you know, pose these conjectures, and they had some intuition, but then somehow she came with a counterexample, right? She was famous for constructing counterexamples. So she was very well known in the field, right? So, you know, I was inspired by her somehow. And then I was fortunate enough when I presented my master work in a conference that she attended. And she actually came and gave me some words of encouragement that I always, you know, I keep it dearly. So yes.
Right. Okay. So role models first. As mathematicians, my role models were my father, first of all, and then my professors at the university. Yes, and there are many of them. But the person who actually changed the destiny and my career and believed in me, and he transformed me, he convinced me to become a mathematician, was my PhD supervisor, Professor Sorin Ciuli from University of Montpellier too. As a female role model, I do have my mom as a role model for my personal life. And then getting back, so yes, my role models are male. Yes, they are all men, and but it's okay. I think it's perfectly acceptable to have you don't necessarily need to have female role models in the end. And as long as there are people who believe in you and they guide you and they inspire you. And then my first research project was my PhD research project was on, and it's still one of my current research projects. So I followed it through for 22 years already now. It's on electrical impedance tomography, which is a non-invasive imaging technique. It's a technique which reconstructs the electrical properties of an object at the interior of an object from measurements of electric currents and voltages performed solely on the boundary. And it's a technology which has many applications in geology, non-destructive testing, but more importantly, it has some medical applications. And if I have the chance a little bit later, then I'll expand a little bit more on the medical application side of this technique. Yeah. It's an inverse problem. It's very ill posed in the sense that little errors in the data on the boundary that you might correspond to big differences in the reconstructed electrical properties in the interior of the object. It's a fascinating subject, and that was my first research project, yes.
Very well said. So, is there a research project that you are working on at the moment? So, unfortunately, we're a bit tight for time, so I'll have to go to the last section. What is your experience as a lecturer teaching mathematics?
It's what gives me energy. I love it. I love meeting the students. I love hearing them protest that something I wrote is wrong. Sometimes they're right, but I love it when I prove them wrong. So, so yes, by the way, this is our mission. What I aspire is that my students, my graduate students, my undergraduate students, all of them will be better than me later on and contribute more than I have contributed. Hopefully, remembering what I transferred to them, transmitted to them, and making it more beautiful than I have. So I bank on them to do big things, right?
So well, this was so far I have been enjoying it a lot, and obviously I'm not as experienced as Irene and Christiana, but I'm still learning, and the students have told me a lot, right? Sometimes you think some topic, explain it, and you know how to pass it on, right? And learning at the same time, so it's been good, and maths department here, I'm very happy to be.
You have something you'd like to say about this?
My experience as a lecturer teaching mathematics, well, it's probably a very enjoyable experience, and the subject does not really matter. What matters is the fact that as a lecturer you are in touch with the young generation and you interact with them, and they stimulate you, and they actually keep you young in some sense, keep your thoughts young, keep your mind active, and and I think that this is the most beautiful part of our job, the fact that we are interacting with students, we are forming them, we are preparing them for life, and not only by teaching them a subject, mathematics in this case, but by educating them and shaping them and reshaping their ideas and creating maybe hopes and expectations for future for them. It's a very noble actually profession, yeah, of teaching, especially at all levels, but especially at university level when you are dealing with, you know, students who are a little bit more mature and they are at the point where their aspirations in life are formed, and it's nice to be able to contribute to this end. Yeah.
Wonderful.
That's all.
So what do you think can be done to attract more women in mathematics today?
Actually, we have quite a large number of women starting and even finishing the course nowadays. In my days, it was different, but now the problem is that these women then either stop doing maths for some reason, or for some reason, for life's reasons. I mean, every woman knows that she's expected to create a serene atmosphere in the house, take care of children. At the moment, for example, my daughter has 2 small children and she's trying to do something, even send an email, and she can't, you know, and she has to, and her children sleep at 11 o'clock at night, even though young. So she's exhausted. I mean, these are hurdles that I think for women it's a bit more difficult, and maybe it's that stops them from you know, their love for the family, their love for, although things are changing, I mean, and I never used quotas, or else, let's say, quotas were never used on me. But I'm not against quotas, because in Norway, for example, I was president of the European Women in Mathematics, and I learned a lot from them. You know, the Scandinavians, they do quotas in everything, even to decide which products to import, which everything they put in quotas. And it was natural for them to put quotas for women. And it was so successful that young children were asking their fathers, can we ever become prime minister? Because the prime ministers were women, you know, many of them were women. So, yes, it's an attitude. And although there is legislation, attitudes are very hard to change. Before, I'm very religious, but before the church had, you know, sort of used to enforce these ideas more. Now they have a problem because the following is reducing, but at any rate. So yes, to change the attitude is not easy, right? And we prove ourselves. Thank God there's the internet. So recognition comes from people who don't know you. Sometimes they don't care whether you're an animal, a woman, or a man. And also we're in the EU now, And the practice in the EU, you know, and even in, say, Norway, which is not part of the EU, but they're very progressive. They influence us. They have influenced us quite a great deal, I notice, because otherwise I used to find it very hard at the beginning. You know, to assert myself as much as I wanted to, but
Yes, I agree with Irene that now in Malta, you know, there are no women doing math, right? So perhaps I don't know what I can, even at younger age, you know, maybe in earlier education, encourage students that show any, you know, aptitude for maths, right? Get the information, although like kids these days have the information everywhere, right? But you know, encourage them, teachers from early education to pursue a career in maths.
Yes, I think, look, we have a lot of female students in mathematics studying at undergraduate level, as Irene said. The problem of young female students studying mathematics, that's not a problem. The problem is retaining them once to pursue further studies or to be interested in careers in research or academia. That's our biggest issue. And as Irene said, there are some personal factors. The women might find a little pressured to establish a family, or not really. They might just, you know, in some sense, go for easier career pathways or career pathways which are advertised as trendy, or they can offer, you know, much more rewarding lifestyles from the financial point of view, and the mentality in order to be able to retain more women in mathematics as in many other subjects, STEM subjects, is the mentality has to change, yeah, and that has to start actually from very, very early age. You know, it's the mindsets of the people responsible for the girls' education choices and for transmitting these gender stereotypes have to change. And I'm talking about parents, I'm talking about kindergarten and primary school teachers. The education has, you know, the mindsets have to change, and the education has to change from that very, very early on. Yeah, it's too late maybe when women, or maybe it's not, but it's a bit too late when women reach us at the university level, and they might already have in mind a career to follow which has nothing to do with research or academia. Yeah.
Yes. You have some advice for girls who are studying or thinking of studying mathematics?
If you enjoy it, do it. Never go for trying to leave a mark. You know, I want to be famous, because it doesn't work like that. What you have to do is enjoy what you're doing, because recognition from peers, this is what makes, say, Polardash famous. His peers always thought, oh, he's, you know, he's wonderful. But recognition from peers comes slowly. Sometimes you have a bunch of papers, you know, they're great, and they start being recognized 20 years later, you know, and cited, you know, all the time then, and then, you know. So it's how much you're cited, it's how much you're recognized, like any other business, say. If you have a product and it's good, but people don't recognize it as good, then it might just as well be bad. True? So don't worry, just enjoy what you're doing. And if you never become famous, you would still have enjoyed life. So that's more important.
Yeah, I very much agree with Irene that, you know, you really need to find, you know, if you like mathematics, do it. Even, you know, you will realize that when you start studying mathematics, there are many areas and you are going to find many areas that you don't like, right? But if you know mathematics is your, you know, is for you, you will find your place, yes. Maybe, you know, it will not be the easiest, but as long as you will enjoy it, you will succeed. So, yeah.
Prof. Sebu?
Yes, well, more or less along the same lines, my advice would be to follow your heart, follow your dreams and aspiration, no matter how hard the journey might seem at times. We only live once, and it's better if we do what we actually like and enjoy as a profession, because we spend a lot of time, most of the time of our life at work. Yeah.
Yes.
So, thank you. Thank you all for joining us today. It has been a wonderful time listening to you talking about mathematics and your journey in life as you've studied mathematics. I think they deserve a round of applause. Now we can have a short 5-minute break, and then we'll move on to the next panel, which will be moderated by Miss Maria Aquilina, who is the event manager of the Malta Mathematical Society. Thank you.
science panel, which are Dr. Fiona Sammoud, who is the head of Department of Statistics, as well as the Deputy Dean of the Faculty of Science, Prof. Pauline Gallia, who is the former head of Department of the Geosciences Department, as well as the first head of Department of the Geosciences Department, and Dr. Deandra Kotayar, who is an astrophysicist and also a data scientist, which is based in London. So, to start off this panel, first and foremost, I'd like to thank you for accepting our invitation and for being with us today. It means a lot to have three women like you. So to start off, as students, we'll be taking on a similar path as the previous panel. Describe a bit your journey as scientists and how mathematics got involved along the way. So what attracted you into science? And did maths please you? Did you find it threatening? Was it part of your choice of career?
Thank you, first of all, and well done for this organization. No, my case, mathematics, well, I always enjoyed it from a very young age, mostly because of my father, who always insisted that we do well in maths and we're always one step ahead. So, we did a lot of problem solving and so on. So that was always a sort of enjoyable thing for me. So it was natural to do mathematics at A level and physics and chemistry at that time. But then it was a sort of series of coincidences or decisions. I never really had, at sixth form, I never really had a set goal in mind where I was going to go because I enjoyed everything. Mainly followed my brother who did a BSc, so I said I'll do a BSc as well. And at that time, it was in the early 70s, you did the BSc was 3 years. In the first year, you did 3 subjects. I had maths, physics, and chemistry. And then in the second year, you dropped 1 subject. So it was a story similar to Irene's because I chose physics and chemistry, and then one of the lecturers, who was eventually my supervisor, called me and said, "What are you doing? Taking chemistry? I mean, you should take physics and maths." So I did. But then I sort of started to gravitate more towards physics and then geophysics and then geosciences. But maths was always there. I mean, maths was always, it's inseparable from physics and geophysics and the sciences. So, it's always an integral part of what you do.
Thank you. Yes, thank you for inviting us, of course, and thanks to all of you who came today as well. I loved maths since I was in primary school. So that was always the first homework that I used to do. Somehow I found it appealing. I didn't like doing compositions, for example. I hated it when I had compositions to do for homework. If I had a deadline, which was a week from today, for example, I would do the composition the latest possible. I mean, I did well in all subjects, but maths was always my favorite. I come from a family where, for example, my father barely knows how to read and write, and my mom doesn't have a very high level of education either. But my mom always tried to help us as much as possible, and that was mostly until primary level when we were, because I have a brother and a sister. At secondary, to fend for ourselves mostly, but because my father had a hard job, especially, he always encouraged us, and my mom always encouraged us that to try to get a good education. My father mainly told us kind of, I work really hard, he had a very tough physical job, so try to get an education so that you don't end up like me. But I mean, now, of course, we have a hard job as well, mentally mostly, but so it's a different type of hard job as well. And he realizes that. In fact, when I speak to him, he tells me, Lalo, kind of, yes, it's also hard, but in a different way. But I always came from an environment when we're strongly encouraged to study and to pursue to pursue a career with a good level of education. And he was also, he always encouraged me to look into careers like engineering. So even though I was a female, being a doctor, all right, was mentioned, but I remember my dad encouraging me to go to pursue a career like architecture, engineering, which is quite unlikely, I mean, as a career for females. Even nowadays, still there is a lot of need for more engineers, especially female engineers. So, I mean, I kept on furthering my studies. I chose maths at A-level together with physics because my main aim was engineering or architecture back then. Then somehow something clicked when it came to choose my A-levels, the undergraduate degree. And I said, well, I don't actually enjoy physics. I actually enjoy maths. Why am I going to pursue a career where I have to use physics? And physics is not really something that I actually enjoy. To be honest, I had chemistry at O-level, and I would have preferred to take chemistry with maths as A-levels. But back then, choosing chemistry and mathematics, I mean, what can you do? I think at that stage, I didn't even know about the possibility of taking a BSc. Now there's more awareness about the possible job opportunities that people can take as well, that students can take. And there are many more opportunities for all types of sciences that you might want to choose. So I decided to choose statistics with maths. Those were the choices that I took for my undergraduate degree. I don't regret it at all. During the course, I decided that I actually wanted to pursue further studies in statistics, but statistics and maths, they're strongly linked. I mean, for example, algebra and statistics, it's widely used. Concepts like, for example, integration, differentiation when you find minimum, maximum. In statistics, especially operations research, we do optimization. Like, for example, you want to devise a strategy to optimize, to get the most profit out of something. That's optimization. You need to maximize the profit. You need to use differentiation there, right? So I can keep on going. I mean, dimensions, so finite dimensional, infinite dimensions. We deal with function spaces. Like what? For example, if you have the regression model, y equals mx plus c. That's a model, you know its form, but that form might not be known. So you might need to find some other function. So you deal with function spaces in that case. And mathematics, I mean, you can't do without it. So of course, you have to love mathematics as well to keep on pursuing something, a career in statistics as well. So I can just keep on going. Sorry about that.
First of all, thank you for inviting me. I hope you guys can hear me well. So I always enjoyed mathematics for as long as I can remember, like primary school, secondary school, and a similar story as to Dr. Fiona and Professor Galia. My parents always encouraged me to follow my passion, even my dad. After I did my levels, I had no idea what I was aspiring to work as or studying further. So I've asked for a counseling session at the University of Malta and said, these are my qualifications. I just enjoy maths and then enjoy physics. And the counselor suggested that I should do a bachelor in maths and physics. And he told me that eventually, hopefully, you will understand what you want to do. Towards the end of the bachelor, that's when I started to realize that I can actually study some form of astrophysics, cosmology and astronomy at the University of Malta, where I did my final year project on theories of gravity. And then I pursued a doctorate in astrophysics, but it combines mathematics, physics, and statistics, which essentially gave me the skill set and the tool set to work as a data scientist. Dr. Samut was mentioning optimization, which is basically what I do almost on a daily basis as a data scientist, to optimize not just, like pricing, but also to understand, which product would sell better, or how to understand the customers better, or the segmentations. So I use mathematics everywhere in my career as a data scientist.
Thank you. It's so great to hear your stories of how you were students and how you gravitated basically towards mathematics and your respective fields. So my next question will be, after ending your era as students, to put it like this, and entering into the research area. So what was your first research project? And was mathematics involved in any way in this?
I suppose my first research project was my master's project. And this was also a coincidence, because when I came to start my master's, it was a master's partly taught and partly research at that time. So there was quite a strong taught component. But it happened that there was a group of German scientists from the University of Karlsruhe. They were seismologists, and they wanted to install a seismic station, a seismograph on Malta. So they came to the university. So the lecturer in charge, he proposed a site at the university. There was an old war shelter. Now there's a small football field, I think. So below it, there was a small shelter, and they prepared it, and this instrument was installed. It was a huge instrument at the time, and recording photographically, and it was very complicated. So they said, why don't you do a research project on this? Fortunately, there was a big earthquake in Greece, which was recorded on this instrument, and very nicely. So computers were just beginning, and there was no computer in Malta. So I went to Germany to use a computer, and the project was analyzing the surface waves from this earthquake, analyzing their dispersion characteristics, and then modeling the structure, the rock structure that gives this dispersion curve, these dispersion characteristics. So yes, so that got me started into seismology, really. People were looking at me strangely, sort of, when study earthquakes and things like that, but it was really the beginning of the new, let's say, period of seismic recording here. And then of course I kept, I had to keep this seismic station going. And then quite late in the day, I was about 33, I got this Commonwealth scholarship to New Zealand, and I did my PhD over there, which was a wonderful experience. And sort of I progressed in seismology over there. But then of course you go into other areas of geoscience and other areas of geophysics. But mathematics, to come to your question, mathematics is an integral part of physics, of geophysics, seismology. I mean, if you come to look at the propagation of waves and layered media, that is an important part, a central part of this. It's wave propagation, it's a mathematical theory of that, and many other things. So if you do probabilistic hazard assessment, it's a theory of probability, and a lot of inversion theory. Most problems in geophysics are inverse problems. So all sorts of branches of mathematics you cannot do without. They are all an integral part of doing geophysics, or which is applied physics in a way.
So my first research project was for my PhD. I worked on what is known as compositional data. When we say data, imagine having a matrix, basically, and in that matrix, you have the rows corresponding to different persons or whatever you're getting information from, and you have the different columns corresponding to characteristics that you're studying. Imagine even, for example, a questionnaire. So the columns would be the questions of a questionnaire. And in statistics, what happens is if you have a relationship in the observations that you have within each row, like what? Let's say we're examining how a tablet medication tablet is made, and we have 3 different chemicals, A, B, and C. Altogether, they have to make up 100%. If you know, if chemical A is 30% of it, chemical B is another 30%, automatically you know the final percentage for the last chemical. So you have what we call a constraint in that case. If you know the first 2, you know the third one. And if you have that type of data, you can't use standard statistical techniques to analyze it. And that's called compositional data because there are compositions, right? Even, for example, our diet, percentage of protein, fat, right? So compositional data, you find it in all aspects of our lives, really. And there are still some problems in that area. And in my PhD, I tackled a particular problem in that field. I'm not going to go into any detail there. Actually, publications are still, because I worked with a world-renowned statistician, and he insists on getting papers published together, and he has a backlog of work. So they're still pending, but we're getting there. It's already 5 years since I finished them, and hopefully at some point we get there. But again, very, very strongly linked with mathematics. Anytime that we're dealing with data, again, as I was explaining, we're dealing with matrices, all right? So anytime that we're fitting some model, like y equals mx plus c, it's a model, it's a very simple model in statistics. You need to do estimation, all right? Because in regression, you have m and c. In statistics, those m and c would say, we don't have the actual population data, we have a sample, so that those M and C would be unknown. We need to estimate them. To estimate them, we need to use matrix algebra, we need to use inverses, all right? So it's really just to give you some basic ideas, clear? But I mean, maths. Without it, we wouldn't do anything at all.
So I guess my first teacher research would have been my PhD as well, where I basically studied Bayesian statistics to understand the noise bias in galaxy data that is then related to the composition of dark matter in the universe. And I used mathematics, both theoretical and also applied. So theoretical to find the solutions, the theoretical solutions for the equations, for the parameters for the unknown parameters that we wanted, but also applied because when you have the data, as Dr. Samut was saying, and you have a model, when you compare the two, you do it in a mathematical way. And you deal with both numbers and letters at the same time. So the letters have meaning, and those meaning then become numbers. So I guess that's where I started the research. Nowadays in my work, I use mathematics to also convert words into numbers. So something like NLP, which tries to understand the text that in a paragraph or in a book or a review, for example, of a movie or something, we literally convert a sentence or words and we convert them into numbers and then, or vectors, and then the similarity of those vectors would link how similar the sentiment was. For example, a king and a woman equals a queen. And that is all done by converting words into numbers. So mathematics is present in my research and every day.
Thank you. Thank you for your insights. The next question will be dealing with your experience, both in academia and maybe in industry, of working in a group or leading a group to solve mathematical problems that arise in your research. So what is your experience of this? How do you manage to convene a whole group of researchers and others like you that are trying to work out such a difficult problem, to put it like this, that you will have to use in order to get to the bottom of the questions that you are asking in your fields? What's your experience of this?
Yeah, first of all, teamwork is very important, and especially in our group, we apply for a lot of projects and work in groups and with other groups, even international, on various problems. But you mentioned industry as well. Our sort of link with industry, in my case, mostly is we are asked to investigate certain structures, for example, especially before a certain project or a large building is going to go up, or a building of importance, and they need a hazard analysis and whether earthquakes will impact this site and so on. So we often do these, we often have these problems where you need to investigate what is under the surface without actually drilling or anything. So that is one of the problems. And again, it's modeling. It's always a modeling sort of problem where we measure vibrations of the ground, just the normal vibrations of the ground, looking at the characteristics of these vibrations as they travel across the Earth's surface, and then modeling the structure underneath in terms of seismic wave velocities and so on, that would give observations. And then again, modeling, imagining that there's a hypothetical earthquake somewhere, and the interaction of this wave energy with the ground structure. So this is also teamwork usually, because even for field work and so on. But yes, it's also a mathematical problem. What I forgot to mention also before that, one aspect of mathematics that is used a lot in geophysics and in seismology especially is time series analysis. So most of the signals that we observe are, of course, time series, graphs of displacement against time or whatever. And that is another very important mathematical aspect, Fourier analysis and spectral analysis and so on, correlation of signals. This is a very important area of mathematics that is used all the time to explain signals of the Earth.
Working with other people in groups. So I think the key is to identify who can do what. So the skills of the different persons, what everyone can bring to the table, so that the work can be done more, I think, it can be done in a better way, in the sense, in a more efficient way as well. I think that as heads of department, especially Pauline, what do you think? You learn to understand more about people's skills and people, so how to get the best out of your colleagues. Well, I think that helps. Having worked with the same people on different projects over the years also helps you to know how to manage project as well. But even if it's a project with new persons, I mean, just understanding what is required. So it's people skills probably that would be mostly needed in this case. And with regards to how to deal with the problem, it's clarify the objectives and then proceed from there. So, and I mean, if it's a problem in statistics, there are so many different statistical techniques that can be used. But according to the objectives, then you decide which statistical technique would be the most for that particular problem.
So usually if it's a problem that is common, then we brainstorm on which technique is best. But what most happen in industry is that the common solution will not be custom for the specific problem of the company. So what we do is we brainstorm and we come up with our own techniques, which means that back in the days pre-COVID, when we used to be in the office, it would literally come down to board writing. So we would write equations and would see like how better to normalize, standardize, and visualize them to see what would make sense. Nowadays, what we do is we delegate. Each one of us, for example, takes either a literature paper or takes the data and starts to try and make sense out of it and come up with metrics, with mathematical equations that have not been done before to satisfy the needs of the company. And then we circle back. So then we brainstorm each other. And usually what we end up doing is we come up with a metric, an equation that would satisfy the specific needs of the company, but as a basis foundation would be based on other techniques that have been utilized in mathematics and statistics for a very long time. But that is usually how we work, especially with remote. We cannot write on a board, but we share notes and we end up writing formulas on a Word document, and then we compare on whichever makes more sense.
Thank you so much. I think one of the best outputs of this panel is that we have a healthy mix over here of both academia and industry. So I think a very pertinent question at this point would be, how do you feel that academia, industry, and even perhaps the public service can blend in well to help solve problems that are basically imminent in everyday life? And how does mathematics in your own research come into play to be able to solve such problems? So for example, we know that Dr. Kutayar comes from a heavily data scientist, to put it like this, background in industry. So you deal with a lot of numbers and such techniques all the time. But for example, we did a bit of research, and we know that you have previously had experience with the public service to, for example, train firefighters and people who are involved in civil protection against earthquakes and other possible natural disaster. We know that Dr. Samut is also involved in dealing with statistics, for example, public service as well as private industry. How do you feel that the work that you do and the mathematics involved in it is important for the economy in general and the livelihood of people in Malta and beyond? What's your view on this?
In our case, in the case of geosciences, I think it's very important to have this link between our research, between the science and other stakeholders, the public in general, and civil government and authorities and so on, because a lot of it is about hazards and risks and to the public and to the economy. So it's not necessarily only my subjects, not only earthquakes and tsunami, but also things like flooding, geological hazards, and so on. So it's very important to keep this link and this interaction with the public. One of the most difficult aspects to get across, and maybe it's more statistical, is the idea of hazard, the idea of probability, of the idea of risk, because natural hazards are described in terms of probabilistic terms, and it is this idea that is very difficult to get across, because people want, the authorities especially want to know, will this happen? When will it happen? How big will it be? And it's something that you can never answer exactly. So you always sort of give these probabilistic estimates and so on, which is very difficult to get across. But yes, you mentioned civil protection. We have a healthy cooperation with civil protection, and some time ago we did a big exercise in tsunami modeling and tsunami alert. So in our case, we ran a numerical model of a tsunami, and minute by minute as it approached the island. And it was a very, very interesting experience to work with the civil protection, because they had very little knowledge of what a tsunami is, and the numbers involved and so on. So it was a good learning experience for both of us. But it's as I said, it's important to maintain this relationship in communicating the science, especially because I think that's a central, a very important aspect. The science and communicating it to whoever needs to. That is the problem very often.
Incidentally, we have a student who is studying weather events in his MSc. And of course, yes, it's about probability and risk. So we also have a student studying on Hubble parameter in astronomy, for example, or so we have different studies going on different areas. With regards to industry or governmental entities, Malta is a small island compared to the countries in the EU, for example. So even we might have issues where the estimates that are calculated for EU countries might not apply for Malta because of its size. We might also have, and in fact, we have very, very good relationships, even, for example, with the central bank, with NSO, MFSA. I mean, even with our students, for example, the central bank and NSO, they offer internships to our students as well. And especially because they see what statistics and the mathematics behind what they learn at university, of course, can provide even to update the techniques that they might be using, the tools that they might be using, to adapt those tools also for the needs of our islands. So they are very, very important tools that they might need to be adapted specifically because of our size. With regards to other industries, for example, financial industries, there is the finding the optimal strategies to optimize a portfolio, for example. Okay, so in that case, statistics plays an important part as well. Betting companies, of course, for example, fraud detection. Okay, so again, mathematics behind that, all right? So the probability of having someone who is attempting fraud, or, for example, to identify persons who might be at risk of being compulsive gamblers, for example. So, I mean, or in medicine, research going on in the medical field, for example, to study psychological effects of persons being given medication over a period of time, whether that medication, so they got a diagnosis, they're being given medication, and whether somehow that medication is helping them even psychologically, right? Over, for example, 2-year period of 2 years. So I mean, in our case, statistics, we can use it anywhere and everywhere. I can keep on just giving examples where our input can give very, very good results for the benefit of society and everyone, really. we're involved. I mean, me and my colleagues were involved in different topics.
I will continue with that because I myself worked in betting and I developed models in anti-money laundering and gambling addiction, detecting gambling addiction before it actually happens. But I guess one of the projects that I'm very proud of where I used heavily mathematics was using weather data to predict the risk that a ship has when exposed to rough weather. So we had to consider cases where with COVID, for example, ships started routing different directions. So to avoid port fees, to avoid some other fees that are expensive, vessels were taking a different journey through the ocean, which meant that they were being exposed to rougher weather. But that doesn't mean that they are at risk. It just means that they are going through rougher weather. Some ships are built for it, some ships are not. And so by building a model based on mathematics and statistics, I could predict the risk of a vessel based on the behavior of the fleet, based on the behavior of other vessels of the same type, but also the evolution of the behavior. And by that, I mean, with climate change, as ice is melting, there are more routes being exposed towards the north part of above Scandinavia, which means that eventually a lot of vessels will start rerouting towards that, going through those journey. So with mathematics, I developed this model that whilst it will penalize vessels that move away from the behavior of their peers, it will not penalize them if they're doing it holistically. So if everyone is going through that route, it's okay. But if everyone is going through that route, but one of them is going through a different journey and then being exposed to rough weather, then the model would basically set an alarm on the vessel name, and the insurance company will then say, hey, why are you going through that journey? You're being exposed to rough weather. You're not meant to go through that rough weather. You're risking a claim. And the idea is that to, first of all, monitor the vessels to avoid claims and avoid tragedy, but also for insurance to know which vessel behaves correctly, whether they would behave for the safety of the vessel or whether they wouldn't care what their vessel was built for and they were just going through different routes. And that is all based on mathematics and statistics in insurance.
Thank you very much. 3 brilliant experiences of how mathematics is really used in real world problems. Now to round it all up, we have 3 accomplished women, researchers, lecturers who have a great experience both in industry and in academia, as in the previous panel. You are all 3 role models for us female students and students of sciences and mathematics in general. My last question for you, what advice would you give to women and students like us who are thinking of pursuing such a career, maybe not necessarily directly into mathematics, but a natural science that leads them to work with mathematics? What would you tell them to encourage them to pursue such a field and make them a bit of courage as well? What's your take?
I think they should, first of all, avoid the question, what will I do at the end of the course? Because that is the most common question that especially sixth form students ask. And realize that studying mathematics and the other natural sciences, it gives you a lot of skills, a lot of thinking skills, problem solving skills, and especially now other skills such as computer skills, because courses nowadays are you know, they cater for new methodologies that we didn't have in my days. So even, you know, computer programming, coding, and so on. So the journey along the way is itself useful. And especially studying mathematics, if they're thinking of studying mathematics, I don't think they should be scared of studying something which will not lead to a direct employment in mathematics, because I think the study of sciences, especially mathematics, physics, and the other sciences, it gives you a certain preparation for several careers, several jobs. So even given that Malta is a small country and there are not as many, even in academia, for example, I mean, we are limited, let's face it. I mean, you cannot, you know, university cannot employ all the graduates that graduate, but there are other opportunities. And so, you know, they shouldn't worry about what comes after. Well, they should worry a bit, but studying the sciences, especially mathematics, gives you a good preparation, I think.
Yes, I fully agree, Pauline. If you ask me if I ever thought that I would be a lecturer at university, for example, when I was doing my A-levels, I tell you, no way. So I just continued to do what I liked, what I enjoyed really, and then things, I mean, it was really exactly, it just happened. So I became a lecturer, and I mean, even head of department. I didn't even ever think that I would become the head of department, really. So, but again, it just happened, and deputy dean, it just happened. And okay, so, but I wish to reassure you that if you do choose mathematics at university, right? So there are plenty of job opportunities available. I mean, if I speak for our students, our statistics, there are so many companies, they keep on sending me emails, internship opportunities available for our students. There are so many jobs available and too few students are graduating, right? So the need is extreme. And our graduates, we can't keep up with the jobs that they just keep on changing jobs, right? The request for these students is huge. And in different areas, right? So whichever area you might wish to work in, literally. And you're also not restricted. You don't have to choose, for example, if you specialize, let's say you do a dissertation in finance, it means that you specifically have to keep on working in finance. No, the skills that you will get at university, they would set you up for a career that you can easily change from one area to another, right? So the mathematical skills that you gain, they give you the flexibility to be able to change from a job to another as well. This also applies to other sciences, of course, but here today we're speaking about maths, but I mean, this applies to sciences in general. So if you like maths, especially, I mean, we're all passionate about the subject here. If you like maths, go for it. And even if you're a female, half of our department, half of the academics are female. The students, mostly male and female, I mean, we have quite, gender balance is quite good there as well at the moment. I believe it's 45%, 55% in favor of males, all right? So we have a number of females that take up statistics as well. So just go for it, and then you will see step by step. Okay, so be informed, all right? But that's it's something else as well. Be informed about the possible opportunities that are available. But if you like maths, I mean, go for it. That's all that I can say. Yes.
I would resonate, like, if you love maths, just do what you want to do. I myself have experienced, you know, from society, why are you doing a PhD in astrophysics? You basically killed your job prospects. It was a burden and the weight hanging over me for 4 years. Little did I know that, you know, like 2-3 years after I finished my PhD, I was in New Zealand and I landed the job while I was still in Malta. And then I landed a job in the UK whilst I was still in New Zealand. So study whatever you choose to study, make sure that you're happy. I am lucky that my parents always supported my choices and they were behind me all the way. Sometimes I wanted to stop, I wanted to give up, and they were, you know, like telling me, this is what you love, you should fight for it. And I just want to say one thing. I know the fear of what will happen afterwards. But when I can tell you, I live in London, and I can tell you that if you go on the platforms looking for jobs, and if you just type in data analyst, data scientist, data engineer, you will have not one or two job opportunity. You will see numerous job offers, and the market is very active at the moment. So I myself have requests from recruiters every single day. It's not a matter of whether you get the job. It's a matter of when you will get that job, or it's a matter of which job you're gonna like. But the most important thing is that you enjoy it, because it's not easy. It's not an easy path. Even when you land the job, it's not gonna be like a piece of cake. But if you enjoy it, it's going to be worth it. And let's say for me, my journey, it's worth it. I'm very happy, and I don't regret one choice.
Thank you. Thank you to Prof. Galia. Thank you to Dr. Samut. Dr. Butaya. Amazing to hear all your stories. You've been an inspiration to everyone here, especially the students who are thinking of pursuing such a career. I would also like to thank our previous three panelists. Yes, of course.
One thing about mathematics jobs.
Yes.
You know? Our graduates from years ago are CEOs, I don't know what they call them these days, CEOs of iGaming companies, or the iGaming companies in Malta, and the programming companies produce software. So with BSc, they're the managers, and they're managing their classmates. So they filled up, and there are, because we didn't mention various formats. You hardly ever see mathematics advertised. We want a mathematician, not the ones I saw. But Ovaletta advertised one for this analysis, and more the border was MSc. That's the only time I saw a job directly for a mathematician. But now with iGaming and programming and software development, there are many. So don't worry about it.
So with that brilliant comment, because it really literally enforced what I've told you every time that I visited the class, either in St. Aloysius, at junior college, and even at higher. We've told you, don't worry about job prospects, because taking a course in the natural sciences will surely lend you such jobs, and not only just one, but you are open for a diverse choice of possible employments that you can take. So once again, I thank our previous panelists as well, Prof. Shriha, Dr. Zamora, and Prof. Sebo for joining us. Thank you all for being with us this evening. We have appreciated greatly your inputs and your experiences, and we hope to have the chance to collaborate with you another time as well. Thank you all. Have a lovely evening, and join us for the questions.
Oh, and then Maria, refreshments.
Don't forget to join us for refreshments right outside. Thank you.